Okay, welcome back to this third lecture in the course on Introductory Quantum Mechanics for Computational or Quantitative Biology. In the previous lectures, we discussed this idea of splitting of the world into a quantum real and a classical realm and a fuzzy interface between these two worlds in terms of time and length scales. And we emphasized the fact that starting building block of biology really are in this diagram located at the interface, and therefore if you want to build a reductionist approach to biology, you have to root your path into quantum mechanics. And we also discussed that if you want to understand quantum mechanics and formulate in a quantum mechanics in a way that is sort of easiest or relatively easier to understand, for us, we are better equipped if we take the opposite path. We start by reviewing how classical mechanics work, and then try to see what goes wrong as we approach the quantum realm. What predictions of quantum mechanics are validated? What are the limitations of classical mechanics? Sorry. And why is there a need of quantum mechanics? So that's one of the goals of the next few lectures would be to review some key aspects of classical mechanics in order to equip ourselves with notions that ultimately will be falsified by nature when we will consider systems that have size which are small compared to the ones where we normally apply classical mechanics. But in addition to that, our goal, our second goal, if you look at the previous lecture, is also to reformulate classical mechanics in a slightly different manner, which emphasizes some concepts and some ideas, and give it a higher priority, a higher ranking in the relevance of the theory with respect to their normal ranking when you derive them from Newtonian mechanics. In other words, we want to ask ultimately the question is what is more general than classical mechanics? What can be found of more general than Newtonian mechanics, which is already present in classical mechanics? So what key aspects of classical mechanics are so general as to survive also in the quantum realm? And by survive, I really mean to make sense or be useful. You see, we are trying to go through some aspects of classical mechanics and identify some key concepts that will remain meaningful even when you will perform the transition into the quantum realm. And ultimately, we want to reformulate in a classical mechanics in a form that is conceptually and so to say epistemologically closer to quantum mechanics. So eventually we want a more, if we want to develop formulation of classical mechanics which makes the transition to quantum mechanics smoother. And by smoother, it means that there are some key concepts and rules that are present both in classical mechanics and quantum mechanics And the basic structure of the two theories will remain the same. And what will change is what specific key concepts are and the rules to implement their evolution in time. Some specific details of the two theories will be different, but the general framework will be, so to say, quite similar or even analog. So that's our ultimate goal for this revisitation of classical mechanics. And of course, everything I've been saying in the last slide or in the analog slide I gave in the previous lectures must sound very fuzzy at this point, because it is fuzzy unless you understand the details, and the details will be provided later. So bear with me for a few moments. Okay, in the previous lecture, we started this journey by looking at the fundamental concept of kinetic energy, potential energy, and their sum, which we refer to as mechanical energy. And I put mechanical under parentheses because sometimes we will just refer to it as simply energy. Today, in this lecture, we are continuing along this line and devise two more concepts which you have been exposed to already in the past, but will play a similar role, will be equally useful like these two, kinetic, potential, and energy, because they will continue to make sense even beyond classical mechanics, and they will exist in quantum mechanics as fundamental entities of quantum mechanics. And these concepts are linear momentum, and angular momentum. Okay, so let's start from the first of the two, linear momentum. Well, this is very easy. A good thing is to start with the definition. Given a particle, the momentum of the particle is defined by the product of its mass and its velocity, which is nothing but the mass times the first derivative in time of its position as a function of time. So that's, if you want, here I can express explicitly my dependency on time, and that's my linear momentum. Why do we want to use this linear momentum? Well, again, what is the need to define the linear momentum of a particle? Well, we follow the same track we have been following in the previous lecture concerning the notion of energy. There are two main reasons. There is one reason that lies within classical mechanics, and it's the fact that energy, momentum, and angular momentum are concepts which turn out to be useful to gain information about the behavior of physical systems without having to explicitly solve the Newton's equation, which is a hard task. So in particular, if you have an energy conservation, then you know that if you bounce a basketball on the ground, he will never come back at a higher location than he was before. If you have a perfectly ideal elastic rebound, it will come back to the very same location. But since you dissipate through air, through the ground, it will likely to come back on a slightly lower location. But will never exceed the height of the initial position unless you push the ball down, of course, if you give it an initial velocity. But assuming you don't, that's an implication. And in principle, this information can be gained directly by solving the Newton's equation. But this is complicated. You have really to solve the differential equation and compute and then provide a number of mathematical expressions. But you can get that for free, basically, by using energy conservation. The initial energy is only potential energy. The final energy will be only potential energy. and therefore be at the same potential energy, and 2 points on the same potential energy are at the same height, period, in a classical gravitational field with constant acceleration. Right. So you see, in this case, energy conservation was the game, and energy conservation was able to make us calculations. It was able to enable us to skip making complicated calculations. The second perspective for which energy conservation is relevant, and energy is a relevant concept, is that it's, while the Newton's equation will not propagate into quantum mechanics, there's going to be no room for Newton's equation in quantum mechanics, there will be a role for energy in quantum mechanics. So the concept of energy, mechanical and kinetic and potential, is more general than the concept of Newton's equation. Although within Newtonian mechanics, the concept of energy is a consequence of Newton's equation. So let me draw a diagram just to express better what I said. In Newtonian mechanics, I have F equal ma, and F equal ma will lead me to define this concept and energy conservation, which I will write as E in the point B is equal to E in the point A, just for us to remember. In quantum mechanics, which I have not discussed, there will not be room for this. There is not going to be any F equal ma, but the concept of energy U and T will be still there, which means that even though in classical mechanics they are less fundamental than the Newton's equation, since the Newton's equation is less fundamental in quantum mechanics, and these concepts are there in quantum mechanics, in some sense, they are more fundamental than the Newton's equation. They are more general, they're broader. And so the same concept applies to momentum. The concept of momentum has this double usefulness. It is useful to solve Newton's equation in a very practical way, without solving physical problem, without having to solve in the Newton equation. So it's useful from the practical perspective, pragmatic perspective, but it's useful also from the conceptual perspective because it will survive the transition to quantum mechanics and will appear in quantum mechanics as a main ingredient of the theory. So same parallelism. So why is it useful in classical mechanics? Well, the point is, the basic observation is that if a particle is not subject to any force, the acceleration is zero. So if F is equal to zero, obviously, which implies that the mass times the first derivative of the velocity is zero, which implies that the derivative time of the momentum is zero. So just as much as you have energy conservation, the energy along a particle doesn't change in time, which we call EA equals EB, where B are two arbitrary points along a trajectory. Now we have three more conservation laws. It's going to be dP over dt, but this time my trajectory is a straight line because it's not subject to any force. However, you should be careful. This law here occurs if forces are conservative while these situations, which are conservation of linear momentum, only occurs if there are null if forces, let me use words, are either null or, better to say, cancel out. There could be many forces, but they might be exactly equal and opposite, so that the total sum of them is 0. So one starts to see that there is a conservation law, and since the conservation of energy was useful, maybe the conservation of momentum is useful as well. However, you see, there are many physical systems in which the mechanical energy is conserved. Actually, all fundamental forces do that. So, you know, in some sense, all of fundamental interactions are energy conserving, so the conservation of energy seems to be a very general principle in nature, so very broadly applicable. While the only, if you have a single particle, the only moment where you can use this conservation law is when the particle is let alone and free, which is a trivial problem. So it's not clear from this first example that this conservation is any useful, because everybody can solve the trivial problem of a free particle that is not subject to any interaction. So there is a deeper reason why the conservation of momentum is actually useful in mechanics. And this is evidence when you consider systems of particles. Now, instead of being general and like physicists normally like to be, I like to be practical. And for me, anything greater than 1 is a system of particles, but equations become much more complicated with indices. So I will consider, for simplicity, the case in which there are only 2 particles. We agree 2 is greater than 1. I don't care to be general. The same thing works out when you have n particles, arbitrary number of particles. So if you have 2 particles, well, we have the mass of the first particle times the acceleration of the first particle is equal to the force that is acting on the first particle. And this force, for example, if the force depends only on position, which could be, will depend on the position of the first particle, but also on the position of the second particle. For instance, I have a particle here with an electric charge and another particle here with another electric charge, maybe opposite, and the force that is acting on particle 1 depends on how far particle 2 is from particle 1, according, say, to the Coulomb law, just to give you an example, right? Or it could be anything else. This is the force, so the modulus of the force will contain an R squared times. Okay, now let's go to particle 2. Particle 2 will have an acceleration. This is the force acting on particle 2. This is a function of position of particle 1 and position of particle 2 as well. And that's F2, F1, and F2. Now, you should consider this graph here. I drawn 2 forces, F1 and F2, and I draw them to be equally large in magnitude and opposite in direction, in sign. So basically they're equal and opposite. So I draw F and negative F. This is not by chance. This is the consequence of the so-called third principle of mechanics. Every action generates an equal and opposite reaction, right? So the big observation is the third law of mechanics says F1 is equal to negative F2 for any position x1 and x2. So if this particle evolve and maybe this particle 2 end up here and particle 1 end up here, there would be different forces, yet they will be still equal and opposite. So with these concepts in mind, we can do one thing. We can sum up these 2 equations. We get a new equation, which is m1, and rather than writing the acceleration, I write the derivative of the first velocity plus m2 times the derivative of the second velocity. And then I will get f1 plus F2, and because of this relationship, this will be 0. So the sum of all the momenta in the system will not change in time. So the change in time of the total momentum, defined as the change in time, as a vector you obtain by summing up all the momenta in the system from 1 to n. I give you the proof for 2, but believe me, it's a straightforward to generalize it to n. This is always 0, no matter what kind of force you have. This is always true. This is always true, but careful, as long as I include all particles. What do I mean by this? Well, look at the screen. I have a particle. It has a velocity, initial velocity. I'm going to drop it. Now, so that means that after I dropped it, this guy has a momentum. It changes its momentum. And then he reaches my hand and stops its momentum. So it looks like the sum of all the momentum of the particle, in this case, there's only one particle, is far from being constant. So is this violating conservation of momentum? I repeat the question. I have a particle here falling down. So clearly, initially, it is 0 momentum. After a while, it has final momentum. And eventually, again, 0 momentum. So it looks like this particle is, in fact, changing its momentum. But there's only one particle, I'm claiming. And if I sum all the momentum in the system, the sum of all this, in this case, the sum of this single particle, should be constant. And it obviously, very obviously, is not. So there must be some, either what we did was wrong, or I'm misinterpreting the principle. And in fact, I am misinterpreting the principle, because this particle here is far from isolated, is interacting with the particles on Earth. So as this particle changes its momentum in velocity, Earth reacts to it, changing its velocity towards this particle. Now, how come we don't notice? Well, we don't notice because the ratio of the masses of the particle dropping down and the Earth are very, very, very different. To be, to be specific, let's assume that some initial position, the particle and the Earth are at 0 velocity or 0 relative velocity, where we could think, in either case, we could write, say, mass of the particle times its velocity, plus the mass of Earth times big V, which is the velocity of Earth. And then they're both 0. Let's make this a sample. It will illustrate the point. And then we look at the later time, and since the sum of these two objects will not change, I could put an equal sign. This is a constant. And so we write the mass at some later time, V, and I call it V prime, plus the mass of the Earth at some later time, big V prime. So which will say that the mass of the Earth at later time will be negative the velocity of the Earth at some later time will be equal and opposite the velocity of the particle, but multiplied by a factor m over n, which is far from 1. So in other words, at the beginning I have the Earth and the particle, and they are 0 velocity. And at the end, I have a velocity v from the particle, v prime, and a velocity here, which I cannot even draw because it would be v prime is equal to negative v big V prime is going to be negative small v prime times m over big N. So if I were to zoom this, now I'm going to zoom by, I don't know, a million, whatever it is, 10 to the x, big factor. Then I would see a small vector of the Earth, v prime. So you have to use the momentum conservation principle very carefully, making sure you include all the particles. But if you do, then you learn something very, very important and impressive. We can study all kind of billiard boards, we can, do all sorts of calculations using momentum conservation. For instance, suppose, I'll give you another example. Suppose we are on ice, and ice means no friction. Just as an example, have a little kid skating towards mom. And when he gets close to mom, the kid will jump in mom's hands. What is the velocity of the mom plus kid system? Well, let's suppose mom has a big velocity that is 0 and a big mass. I hope moms will forgive me for calling them having a big mass. And let's suppose the kid has a small mass and a certain velocity v. Well, can we predict what will be the final velocity of the system once the kid has jumped in the hands of the mom? Once again, we can. How? Because we know using sum of momentum of all the particles being constant, we can say that the initial velocity of the kid is m times v, the velocity of the mom is 0, and this must be equal to the sum of the system with the mass given by the two, mama and kid, and a new velocity v prime. And given this, we discover that v prime will be v times m divided by m plus m. So in particular, if I collect out m, I can do this. So if mama is so much bigger than the kid, it will not move much faster after the collision. Okay. So we can play along with this principle altogether. But I think we made a point that the conservation of momentum enables us to obtain prediction without solving Newton's equations in certain situations. Now, what about angular momentum? Now, when it comes to angular momentum, this is one of the critical points in the physics education. I would say most of students get involved with conservation of momentum and angular momentum at the high school education already. And I would say a fair amount of them understand conservation of linear momentum, the one we just discussed. But when it comes to angular momentum, there's something more complicated to grasp. And as a result of that, very few people really understand angular momentum conservation without a thorough physics education. So I'm in a somewhat more difficult situation here to review the concept of angular momentum conservation. But we will see that the role of angular momentum will be crucial in quantum mechanics, essential to understand the behavior of matter and molecules. There's going to be no way we can understand chemical bonding or orbitals without the concept of angular momentum. So we have to make an effort to digest that. So let's start as before by considering the case of a single particle to begin with. We have the angular momentum of a single particle is defined as its position vector product with its linear momentum. Okay, so, you know, I guess you've all seen this symbol before, and it's an operation between vectors that returns another vector. And there are many ways to cook up rules on how to evaluate this. I want to give you two ways of evaluating A cross B, so let me make a parenthesis or a detour. I have a vector A and a vector B. How do I compute the product? Well, there's way number one. It's the graphical one. You draw vector A and you draw vector B. Now, given two vectors, you can always find one plane that contains them both. See, take one vector in one direction, one vector in another direction. That's pretty random. I can always find one plane, okay, one plane that contains both. So I'm drawing this plane as the board where I'm writing. Now, the vector resulting from this multiplication, let's call it C, will be directed orthogonal to this plane. So in this case, it will come out of the plane, either in this direction or in that direction, depending on the side. But it will be lying on the direction orthogonal to the plane. So that sets one piece of information. And its magnitude and sign are determined by the rule so its modulus, if you want, is determined by the product between A and B and the sine of the angle between them. Finally, the sine, whether it will be coming outside or down into the wall, is determined by the screwdriver or the upper Bottner rule or the right-hand rule. You probably have seen of that. I like the right-hand rule. Right-hand rule, you put the first thumb in the direction of the first vector, the index in the direction of the second vector, and then you get the direction. In this case, it's going inwards. And vice versa, if I was to switch the order of the vectors in multiplication, B cross A, I would get a mountain. You choose your rule. Doesn't matter, as long as you can compute the direction in any way. The other alternative is, you know, imagine to use a screwdriver that you make it turn from the direction of A to B. And if it goes from A to B, it's going to go inside. If you go from B to A, it's going to go outside. Well, that's another equivalent rule. There is a different way in which you compute inner product, and is no, that is not gonna. I'm not gonna discuss that right now. I'm going to discuss that mathematical way of computing inner product slightly on later on in this course. Okay, so that's as much as one particle. Now, what happens to the derivative in time of the angular momentum. Again, remember, that's always the same scheme. We define a quantity and then we ask, under which condition is this quantity conserved? The mechanical energy is conserved whenever the particle is subject to forces that are conservative. The momentum is conserved when there is no particle, no force for a single particle, or whenever you have a system of particles, no matter what forces there are inside, the total sum of momentum is conserved. Finally, let's do the same for the angular momentum. Let's ask, under which condition this guy is zero? Well, to do that, let me take its derivative. Well, I can take the derivative of the first particle with respect to time cross E x plus x cross dp in dt. Now, the first of these two terms is nothing but the velocity cross the momentum. Now, the velocity and the momentum are parallel because the momentum is proportional to the velocity, which means that the angle between them is zero, and which means that this guy is obviously zero. This is zero because velocity and momentum are parallel. Therefore, the outer product or cross product depends on the angle between them. The angle between them is zero. The sine of the zero, sine of t zero is zero. This is zero. The second term, now I remind myself that the derivative of this is nothing but the derivative of the mass times the velocity, and the derivative of velocity is the acceleration, which means by Newton's law that this is the force. So we discovered this interesting relationship, which is the momentum of a force, right? The torque. This is called the torque in English. Now, whenever the torque of a particle is zero, the torque of the forces acting on a particle is zero, then the angular momentum of that particle is conserved. So, for instance, when F is parallel to, I wrote R, but I meant really X, to X, like in centripetal or centrifugal forces. Gravity is the centripetal forces because it points in the direction. The sun attracts the position of the earth with respect to the sun is given by X, and the force is given by F, which is proportional as it lies along the same direction as X, as a result of which the earth around the sun proceeds along a motion that conserves the angular momentum. So the energy is always of a single particle is conserved as long as the force to which this particle is conserved. The momentum of a single particle is conserved as long as there are no forces, net forces acting on that. And the angular momentum is conserved as long as the forces are centrifugal or centripetal, or in other words, if there is no torque. But this is one important result. But the second important result is that as we did for any force now, any force, not just centrifugal force, any force, the total angular momentum, just as much as with the linear momentum, is always conserved. And I don't go through the proof because it's exactly the same as the one we did for the linear momentum, just a little bit more manipulation. But again, the key point there is the third principle of mechanics, that when you sum quantities, you cancel out the contribution of forces that are equal and opposite. So angular momentum is conserved. So the question is, what do we need angular momentum conservation for? Well, we'll see one reason we will use it to simplify mathematical problems when we try to develop a classical theory for the ideal draft. But that's a little bit too advanced for this lecture. I will give you equivalent examples of the usefulness of the conservation of angular momentum. And I'd like to say this. I mean, people talk about the ballerina closing the, if something rotates at a given angular momentum, or given velocity, angular velocity, and then all of a sudden change the shape. And in order to preserve angular momentum, it has to rotate faster. I'm sure you've seen this already in your previous education. I'm going to give a totally different example, which might sound a little bit counterintuitive to you, but this is a question that I was always asking the students when I was giving the exams on classical mechanics. And the question was, you are an astronaut in space, and you end up in the opposite direction with respect to the space station that sits behind you, and you want to turn. How do you do? If you are in water, it's easier because the water is a viscous system. You can push things away and you get pushed by that. How do you turn in space? And it's quite simple to understand that, for instance, if you do this in space, then clearly your arms will rotate in this direction, generating angular momentum in this direction. But in order to compensate, the rest of your body, all the other particles have to rotate in the opposite direction in order to conserve angular momentum. So the body will turn in this direction, and you end up in a configuration where your legs are up and the head is down. So you see, the concept of angular momentum conservation is powerful as it helps us to solve problems without having to solve Newton's equation. So, in conclusion, in this set of lectures, we derived three fundamental conservation laws. One of them is a scalar, not a vector, is the energy conservation of total mechanical energy of a system. The other one is the conservation of total linear momentum of the system and the total angular momentum of the system. And these are true for any force, for any kind of force, without making any description. And in addition to that, we derive specific laws that are valid only under certain conditions. The energy of a single particle is conserved as long as the force is conservative. And typically, a conservative can be that it makes no work, or it's constant, or is radial. It's again along the displacement. Again, like the Coulomb force, the gravitational force. For a single particle, the derivative of momentum is zero only if the force is overall, the net force acting on the particle is zero. And for the single particle angular momentum, it is conserved as long as the torque of the force is zero, which is again true for radial forces. Okay, these concepts are fundamental, and I will use them both in the context of quantum mechanics, but much before, I will use them in reformulating classical mechanics in a powerful, conceptually sound way, and I will use them in our effort to show what goes wrong with classical mechanics. In particular, we will use this conservation law when we will be trying to understand the existence of atoms based on classical mechanics, only to discover that according to classical mechanics, atoms shouldn't exist. So the very fact that we exist is a proof that at the atomic scale, classical mechanics is not an accurate law of nature. Okay, and I want to close this lecture, but I want to close this lecture with a question rather than with the answer. What is a physical theory? Now, everything that I've said so far is unrelated to this question. This question is something I throw on the board, which simply looks like a motivation for the next lecture, where I will reformulate classical mechanics in a different formalism. But I'd like you to spend a few minutes in asking, okay, if I were to answer my little brother who's just in elementary school and said, brother, what is a physical theory? What does physics mean? What is a physical theory? You talk about that, but what is it? What kind of answer would you give? I'd like you to think about this question, because next time we'll start from this question and discover that what we think makes sense as a physical theory, such as Newtonian mechanics, contains some loopholes here and there and some things that are subtle, and we need to think harder to understand what it actually means. But, you know, this is for the future lecture. And so if you want, this is a teaser for the next step in this journey. Goodbye.